Good evening, everyone, and welcome for today's talk. So today we have with us Dr. Sourav Chatterjee from TIFR, and I would request Dr. Ravi to kindly introduce our speaker for the day.
Thank you, Prachi, and thank you, Sourav, for taking the time to give this lecture. So Dr. Sourav Chatterjee is now a professor and a reader, I guess, in Tata Institute of Fundamental Research. And I think I've known Sourav since the last 13 years or so when we met at Northwestern University, if I remember correctly. And Dr. Chatterjee is an expert in a variety of topics, actually, specifically on the dynamics of exoplanets, architectures, planet formation, and also, I believe, in stellar astrophysics and stellar dynamics. Just like my background with gravitational waves and astrophysics, I think Dr. Chatterjee also has a significant background in compact object astrophysics and gravitational wave astronomy as well. However, he's also an expert in this planet formation and exoplanet architectural dynamics. So he's going to talk about exoplanet multi-planet exoplanet systems. So Sourav, whenever you're ready, please go ahead.
Thanks, Ravi. It's great to we know each other for a very long time. It's always really nice to see you. And it's a great pleasure for me to speak at the PKC Exoplanet course. Can you all hear me?
Yes.
Yes? Okay. So today I will be talking mostly about multiple exoplanets. And you have, in previous classes, you have learned about the different detection methods and the demographics and atmospheres maybe. So today I will mostly cover planet formation a little bit at a very pedagogical story-like level. And then I will talk about some of the exciting things that can happen after these planets form if nature creates multiple planets in the same system. Okay, so let's go ahead. So I like starting with this quote from Giordano Bruno. He was a philosopher, and back in 1584, he said that there may be countless suns and countless Earths all rotating around their suns. Of course, by saying this, he did not do any favor to himself. He was burned at the stake. But now we know how true his prediction was. So currently we know of more than 5,000 confirmed exoplanets, about 10,000 more planet candidates waiting to be confirmed. Many of them probably will be confirmed. More than 1,000 planets that are smaller than the Earth. And you, from the detection method course, you probably have seen that the smaller the planet, the harder it is to detect. So it's really extraordinary that we have detected more than 1,000 planets smaller than the Earth. These planets are in more than 3,000 multi-planet systems, and several tens of these planets may be potentially habitable. Okay, so this is extraordinary data set, and these planets are teaching us a lot about what we did not know about planet formation, and after they form, how they evolve for billions of years, after which we see them today. Okay, so the plan for today is first I will talk about the very basics of planet formation, different stages of the planet formation. And I have to warn you that this is the most uncertain aspects of planets, period. Okay. The reason is not because we are not trying. The reason is it's just really, really hard problem to solve. And it's really hard problem to solve, and it's very hard to get observational constraints on these different stages of these of formation. Then I will talk about after they form, how their orbits evolve, or at least what we think about the evolution, how the evolution goes. And then I will intersperse in different stages of this talk, I will talk about 3 selected stories about some mechanisms that I believe must have had key contribution in shaping the properties of the exoplanets that we observe today. Okay, now the selected stories are going to be biased in the sense that I have selected the stories where I had direct part in it. Okay, so this is by far not an extensive overview of all the different theories that exist out there. It's just not possible to do that in one talk. Okay, so let's start with this cool movie. This is basically showing you how we are detecting more and more exoplanets as a function of the year. Okay, so at the beginning, before 1995, that was the first planet around a sun-like star. There we knew about some planets that orbited around pulsars. So these are dead stars. Okay, but after 1995, of course, it became really interesting to find planets around sun-like star. And as you can see, every year we started adding more and more planets on this figure. Okay. And very quickly, you will see that the Kepler space satellite will start giving observations, and you will see suddenly there will be a huge jump in number of planets right there. You see? So one thing that I want you to notice, so this is something probably you have seen in observational methods. You see this trend. So if you go outwards in orbital period, then you see fewer and fewer lower mass planets. This is probably an observational bias, almost certainly an observational bias. But what I want you to notice is that the mass of the planets we are detecting are all the way down to below Earth mass planets. And there is a huge diversity of planet properties. So there are these small planets, low mass planets. Then there are these really high mass planets. These are the giant, so-called giant planets. We will learn a lot about this in the next few slides. And then there are also these planets. These are relatively farther away. Okay. And if you want to ask, okay, so we have detected all these planets, but where are they with respect to the sun? And if you take a look at this, so this is all these different dots are planet host stars, and the center is the sun. So we are looking out and seeing all the planet host stars. And this cone is basically the Kepler field of view. That's why it is like lots of planet detections along this direction. But overall, you see that wherever you look, there are stars with detected planets around them. And in fact, we now believe that almost all stars have planets around them. And it is really essential to figure out the planet formation process and answer several interesting questions. For example, how what are the processes that shape the properties of the planets that we observe today, whether or not the solar system is unique, all that kind, all these very basic and interesting questions regarding our origin. Okay. So, roughly speaking, the planet formation process goes like this. So you have a star, and it has a protoplanetary disk like this. And inside this protoplanetary disk, you have, so this protoplanetary disk is mainly gas. And then inside this, you form planets. you go from rocky particles. So initially you go from dust to rocky particles, then there can be icy particles, and you somehow grow and become protoplanets, okay? So you go from something like this to something like this about 10 million years later, okay? So in roughly about 10 million years, you already have a bunch of small planets we call terrestrial planets. Terrestrial means Earth-like, okay? So Earth-like planets, then there are these giant planets, and there is a lot of small things that could not grow and become planets, okay? And this is the processes involved. We have basic idea of what processes may have been responsible in forming these planets, but the devil is in the details, and the details is not quite pinned down, okay? So there is a lot of uncertainty in the details. And depending on the details, the properties of the planets can change. And that's why it's very interesting to pin down the details, but we have not been able to do it so far. Okay, so why is it so hard? The reason, well, one of the reasons is that the ranges in length scales and time scales involved in this problem is just mind-bogglingly huge, okay? So let's take a look at the length scale involved for planet growth, okay? So you're going from dust, that is roughly micron size, to something like 10 to the 10 centimeters, okay? So that is planet size. So that is a 14 order of magnitude growth. If you think about the time scales, so the formation of planets happen over several million years. The orbits of the planets are between hours to years, and the dynamical evolution where the different planets in different orbits can interact with each other through gravitational interactions, that happens over billions of years. So the range in time scale as well as length scale is just enormous, and it's very, very hard to create models that can go all the way from dust to forming planets. And the problem becomes harder because it is almost impossible to look at young stars with protoplanetary disks and really see inside these protoplanetary disks and say a lot about, say, put strong constraints on the different sizes and where the planets are forming, where the dust is becoming bigger, etc. Okay, but we are making big strides, and I will not talk about what are the important observational breakthroughs that had happened in recent years. If you want to know, you can ask questions later, okay? So in today's talk, I will basically tell you stories that we think are relevant for the planet formation process, and what are the key physical processes that are responsible to go from the dust to planets, okay? So let's think about how can we go from dust to rocks, okay? And we are talking about a growth from about a micron to about a centimeter. And this is just a schematic diagram of what may be happening. So let's say that this is the gas disk, and in the gas disk, there are these red things that are basically dust, and gravity is pulling all the dust to the mid plane of the gas disk, okay? Now the question is, if dust is embedded in the gas, then what happens to the dust? So the way to figure that out is by looking at the so-called friction timescale, okay? So this is a timescale over which the motion of the dust particle in gas will be significantly changed because of drag forces in the dust. So this is the exact same physics as how dust settles on your floor. Okay, so in a room, dust is everywhere, and some of it is subtended in the air, and then the random motions in the air is giving drag forces to the dust, but gravity is pulling it towards the floor. And at some point, the dust will come and reach the floor, and it will be piled up there. So in a protoplanetary disk, dust is basically settling to the midplane of the gas disk, and that's where it will pile up. And if you look at the frictional time scale, it's really, really short. That means that dust is very well coupled with gas. What does it mean? It means that it will not feel an acceleration, rather than it will reach a terminal velocity very quickly. And with that terminal velocity, it will come and reach the midplane. And if you can estimate what is the rough time scale for the dust settling to the midplane, and that is roughly 10,000 years. Okay, so I say that planet formation happens over few millennial time scales. So 10,000 years is very, very short compared to the planet formation time scale. It's fantastic. We understand this process rather well, and dust comes and settles in the midplane of the protoplanetary disk. And we expect that now planets will form at the midplane of the protoplanetary disk using this dust that got settled. Now, as the dust settles, so I'm here I'm showing you time in the x-axis, okay? And this is the size. The bottom panel is the size of the dust that is settling in the midplane, and the top panel is the vertical height, the vertical distance from the midplane of the dust, okay? And you can see that starting from different initial sizes, so 1 micron, 0.1 micron, 0.01 micron, it will take different times to reach the midplane. And as it is reaching the midplane, different dust particles will stick together and become slightly bigger. And by the time it reaches the midplane, it attains roughly centimeter size. Okay, and this time scale is 100 years to 100,000 years, depending on exactly where you are doing this. So now you have dust that may have grown a little bit, and through electrostatic forces, the dust can coagulate quickly and become centimeter-sized objects. And by the time it has reached centimeter-sized objects or rocks, it is already at the midplane of the protoplanetary disk. But now something really crazy happens. So now the solids are not tiny, so they are not coupled with the gas, because that's why they have sunk, and that's why they have reached the midplane, okay? So now we are going to talk about what happens to the centimeter size objects, and how do I go from centimeter size objects to 10 kilometer size objects, okay? So solids are now decoupled from gas, moves faster than the gas. Why? Because gas has pressure, okay? So if you solve the equations of motion of something that has pressure, and pressure will be different at different distances from the star, then anything that has pressure will move at a different speed compared to the Keplerian speed around the star, okay? So if the gas is moving not at Keplerian speed, and the solid that is decoupled from the gas, not moving with the gas, is moving at a Keplerian speed, then there will be a relative motion between the gas and the solid, okay? We can estimate what the relative velocity should be, okay? So let's say that Vk is the Keplerian speed. And let's say that the gas pressure goes as a power law, r to the minus n. So as the distance from the star increases, we expect the pressure in the protoplanetary disk to decrease. Okay, so that's why we are using a power law. If that is true, then the gas, the azimuthal velocity of the gas parcels will be the Keplerian speed of the solids times 1 minus this quantity. Okay, so what is this quantity? This n is the power law index on the pressure, and this is the sound speed, and this is the Keplerian speed square. Okay, so basically, if n is positive, then gas parcels will move at a lower speed compared to the Keplerian. All right, with me so far? All right, if you're lost, please type a question in the chat box, okay? So if we have a difference in speed, then the difference in the speed is simply the Keplerian speed minus the gas azimuthal speed, and that is roughly 0.004 times the Keplerian speed. So the fractional change or fractional difference between these two speeds is really tiny. It's 0.4% of the Keplerian speed. But the Keplerian speed of solids is so high that even that comes to about 100 meters per second relative speed for Sun-like star at 1 AU. Okay? Now imagine you have a wind on your face at 100 meters per second. It's not comfortable at all. It will really push you back, and it'll be very hard for you to walk. And the same thing happens for the solids. So this headwind extracts energy from the solid's orbit. As a result, it spirals in towards the star. Okay. And if you do the calculations using reasonable numbers for the properties of the conditions of the protoplanetary disk, for a meter-sized solid at 1 AU from the sun, the radial velocity, so since it's spiraling in, it will have a radial velocity. The radial velocity of the solid is such that within a few hundred years, it will fall on the sun. So of course, the calculation, it's not exactly this. I am making a lot of assumptions, but these numbers are order of magnitude correct. Basically, if you have a meter-sized rock at 1 AU from the sun in a typical protoplanetary disk, because of this headwind, it'll fall on the sun in about 100 years. Okay, so that is a very short time scale, and this has been a known problem of creating planets. So if all the solids, as soon as they become rocks, go and fall on the sun, then how do you grow from rocks to planets? Okay, so that is the problem. We know several ways to actually stop the rocks from falling to the star. So one of these ways is simply noticing that exactly whether the solid will go inwards or outwards, that depends on the value of this power law exponent. So if n is greater than 0, if pressure is decreasing as R is increasing, then the solid suffers a headwind. So as a result, it goes in. However, if in some place, for some reason, the sign of n changes, that means pressure is increasing as R is increasing, then of course this will become a tailwind. And solids in the mid plane will try to increase their orbital size. Okay. So for example, if I plot the log of pressure as a function of log of distance from the star, then if the black curve is the log of pressure, then nothing is going to stop the solids. They will all move inwards. However, if for some reason you have a situation like this, the red curve, then on this side, solids will move inwards. It will have a headwind. However, on this side, it will have a tailwind and the solids move outwards. So it will create, this kind of pressure profile will create a trap where you can entrap all the solids that are just moving around, okay? And if you can successfully do this, then more and more rocks will come and get trapped in this location. And if you have a high enough density, so that is this quantity, this sigma, capital sigma, if you have a high enough surface density of these solids in a tiny ring of a distance from the star, then all these rocks can gravitationally collapse and form a large object. Okay. If you take reasonable numbers and do the calculation, like exactly when this collapse may happen, and if collapse happens, then what kind of mass do I get, and what kind of size do I get? So that is the order of magnitude calculation I have done here. So if collapse happens, then you can grow roughly 3 times 10 to the 18 grams. This is equivalent to roughly 10 kilometers. And we also know from doing the calculation correctly that the collapse time is roughly 1 year. So that's really quick. So in principle, if you can create these kind of pressure traps, you can very quickly grow from centimeter to meter size all the way to 10 kilometer size. Okay. However, the details of exactly where this can happen, what is the rate of supply of the rocks, can you have persistent traps, or before it can reach the collapse condition, the trap will just evaporate. All of that details is very uncertain, and people are all over the place are actively working on it. Okay. Any quick question after this part? Okay. All right. Feel free to type in the questions. I'm keeping an eye on it. Anyway, so let's move on. So we now are at roughly 10 kilometer objects. Okay, 10 kilometer solids. What happens after 10 kilometers are reached? So these are called planetesimals, by the way. And we believe that planetesimals grow via collisions. Okay, so you have multiple planetesimals that are growing all over the place, and they're orbiting the star. There is also the gas is around, and they just find each other, collide with each other, and grow. And there are actually 2 phases of growth. Okay, one is called the runaway phase. In the runaway phase, when the planetesimals, the mass is small enough such that, so imagine that this is a planetesimal that is just moving around in a sea of rocks. Okay, so when the mass of this planetesimal is not very high, such that its presence is not significantly changing the velocities of the rocks, then it can grow very fast. And this is called a runaway phase. And in that runaway phase, the rate of growth of the mass is proportional to the mass itself. Okay, so the higher the mass of the planetesimal, the faster it grows in mass. Okay, so that of course is the runaway process, and this is a becomes richer scenario. And if this process goes on, then it will form only one monolithic giant planet and not multiple planets. Okay, so of course this assumption breaks down at some point. So the key assumption there was that the mass of the planetesimal is small enough that it is not changing the velocities of the rocks around it. Okay, but that of course breaks down when the mass is sufficiently high. The gravitational interaction between the growing planetesimal and the rocks can significantly stir up the velocities or random velocities of the rocks. As a result, the planets cannot grow beyond certain point. Okay, and that certain point can be captured by the so-called isolation mass. So basically, anything that it could collide with or grow, it has already collided with, but it has grown in mass so much that the other rocks have high velocity compared to its escape velocity from the surface, and these rocks will not go and get collided or accreted to this planet. Okay, so this is called the isolation mass. And if you do order of magnitude calculations, the mass that you get is roughly 9 Earth mass at the location of Jupiter. Okay, so that's all good. We have successfully reached from 10 kilometers to about 1,000 kilometers. That's the terrestrial planets regime. Okay, now how do you grow from terrestrial planets to giant planets? Okay, so that is a growth in mass by about 2 orders of magnitude. You're going from roughly 1 Earth mass to about 100 Earth mass. Okay, so Jupiter, by the way, is roughly 300 Earth mass. So there is one question here by Sankar. Is it safe to say that the asteroid belt between Mars and Jupiter a result of this oligarchic phase of planetesimals? That's an excellent question. So I think the asteroid belt between Mars and Jupiter are relics of the things that did not go to the oligarchic phase. Okay, so the planets grew through the runaway phase and then oligarchic phase, and then later on acquired some atmosphere. That is what we are going to cover right now. The asteroid belt objects, the Kuiper belt objects, the objects in the Oort cloud, the small things, so these remained planetesimal size. These did not grow to become protoplanets or planet size. Okay, so these you can think of the Kuiper belt objects as failed planets. Okay, failed objects that could not grow enough to become planets. Okay, so now we are going to talk about going from terrestrial planets to giant planets. And for this, we really need to understand the concept of Hill sphere. Okay, so Hill sphere is the radius of influence. So if you have a star here with some mass m star and a planet with some mass mp, then let's say that there is some distance from the center of the planet called RH. And let's say that this is the distance within which the gravitational force due to the planet is larger than the tidal force due to the star. Okay? So within this radius, the planet's influence on another massive object will dominate over the star's influence. Okay? So if the planet is about a distance a away from the star, then the Hill sphere goes as a times mp over 3m star to the power 1/3. You will see why this is important to remember. So remember that as the planet is growing, it is still embedded in a gas disk in the protoplanet. Okay? So imagine that this is the planet that I have grown, and let's call that this is M core. And let's say that this radius is the Hill radius around the planet. And this brown stuff is just gas, okay? Gas in the protoplanetary disk. That's where the planet is growing. So all the gas that is within this dashed line will be captured by the core, okay? Because this gas parcels will have the core will have a higher influence on these gas parcels than the star. So once you form a core, it can acquire an atmosphere up to its Hill radius, and this is gas. If gas cools, its volume decreases, so that means you can have more gas falling inside this sphere, and as a result, the atmosphere mass grows. So if you can keep growing the atmosphere, at some point, the atmosphere mass becomes so high that the atmosphere becomes unstable and gravitationally collapses. Okay? And that's how giant planets form. And this happens rather quickly. And of course, as you can see, it goes from roughly 1 Earth mass to 100 Earth mass or even more. So by the time you form a giant planet, through acquiring a large mass of atmosphere that collapses under its own gravity onto the core, the mass is dominated by the gas, and the core is only about 1% of the total mass of the planet. So there are some other questions. Okay, Megha, I will take this question later, okay? So let's move on. I will not forget, I will take this question later. The other question Sri Krishna is asking, is the Hill sphere similar to the Roche limit or a Roche lobe? Very good question, Sri Krishna. Yes, indeed. So the Roche sphere or Roche lobe is more often used for stellar binaries or stellar systems. Hill spheres are used for planets. There is a very specific reason for that. The functional form for the Hill sphere and the functional form for the Roche lobe is obtained by making different simplifying assumptions. Okay, so Hill sphere, the derivation of Hill sphere assumes that the planet mass is small compared to the stellar mass. Okay, Roche lobe, in the Roche lobe case, it does not make the assumption, it makes a different assumption. So that's how these two things are different, but but the idea is exactly the same. You are looking for roughly an equipotential surface between the two massive objects. All right, so now we have gone from dust to planets of different sizes. Okay, now we come to what happens after you form the planets. And we are seeing really, really huge number of multi-planet systems. And this is just a really fascinating movie made by Ethan Krauss. So all the dashed lines are showing you the scale of the solar system planets, and all the colored dots are showing you real known exoplanet systems. Okay, as you can see that the exoplanet systems can have many, many planets in very, very compact orbits, very close to their host stars. Okay. So what happens after you form these planets and you form multiple planets in the same system? Before you get there, let's ask the question, how do you even form them in such a compact orbital configuration, whereas the solar system did not form them? Okay. So what are the problems in it? So without getting into the details, there are two competing planet formation scenarios, let's say, okay? And these two scenarios are still competing with each other, okay? There is no clear winner yet, although I am slightly biased towards formation in situ, okay? So what does it mean? So maybe you form all the planets, and then through disk interactions, you just send them very close to the star. Okay, there are several problems in it. We do not see. So if that happens, then you expect the planets to have very specific ratios of orbital periods, or a large fraction of the planets should have very specific ratios of orbital periods. These are called orbital resonances. We do not see these things, okay? On the other hand, if the formation in situ idea basically says wherever you see the planet today, it was created using the material that was available around that same location. Okay, clear the difference? But the problem with in situ formation is you need to have a large reservoir of solids very, very close to the star. And it is not very easy to actually figure out a plausible way how you can have such a disk that has so much solid so close to the star. So this is where I will tell you about a selected story where I was involved, okay? And this is an idea that we propose that can explain the compact orbits of the multi-planet systems without using what used to be a problem. Remember, I told you about the meter-sized barrier problem. So the fast radially drifting solids. So using that problem, we actually tried to solve the issue of solid supply very close to the star. Okay. Now, don't get scared with all these different things. It's roughly the same kinds of properties that I have already talked about. So this is roughly this is the pressure in the gas disk. This is the relative speed between the gas and the rocks. And this is the radial drift time scale. Okay, so if you use all of this, it doesn't matter what the other different things are. The main thing that matters is it depends very strongly on this quantity alpha. And it is the drift time scale is really tiny, so roughly 40-ish year at 1 EU. And what to notice is that the orbital time, so the typical orbital period of solids, is much less than the drift time scale, which is much less than the disk lifetime. Okay? And we talked about how pressure traps can be sites of planet formation. We said that And this is observationally motivated. So if you have a star very close to the star, it will ionize the gas enough, which will give rise to MRIs. Okay, so this basically significantly decreases the pressure there. And beyond that radius, where the ionization fraction is not as high, there is we call it the dead zone. So this is the MRI active zone, this is the dead zone, okay? Now, at the dead zone inner boundary, you expect the pressure profile to look like this. So the pressure decreases with increasing R outside in the dead zone, but in the MRI active zone, because of the MRI, the pressure sharply drops, okay? And you know, whenever this happens, it acts like a trap. And this is where all the solids can come and get trapped. So if you create a rock anywhere in the disk, it very quickly comes to the dead zone inner boundary, and it comes from all over the place and gets accumulated at the boundary, which creates a ring of solid enriched area. And then you essentially collide and grow and form a planet there. Since you have formed a planet here, now the disk is less dense, so the ionizing rays can go a little further, and you form another solid enriched ring a little further, okay? So that's how you form all the different planets from inside out. And we actually call it the inside out planet formation scenario, okay? It has many interesting desirable properties. Let's not get into the details of this. Let me simply show this thing. So this is as a function of the distance from the star. I'm showing you the mass, expected mass of the planets. So there are many different lines, but all that's relevant for this talk is that all the observed planets, so these are the dots and the squares and triangles, they are populated between this blue dash line and the red solid line. Okay, so even without making any big assumptions, if you simply use semi-analytic calculations based on the stories that I already talked about planet formation, we get roughly the same masses, roughly the same mass to mass to distance from the host star relationship. Okay, so that was a very quick fire selected story of how you form compact multi-planet systems. Let me take some questions here. So Sri Krishna, your next question I will take later, okay? This is not part of the flow. Okay, so let's say that you have formed planets, and how we want to know how the orbits evolve after you have formed them. And the planets can evolve in two qualitatively different ways. So one is, while the gas disk is still present, then there can be one situation where the Hill sphere is smaller than the disk scale height. Okay, what is the height from the top of the protoplanetary disk to the mid-plane of the disk? When this happens, we call the planets decrease their orbit through the type 1 migration. So you are seeing a planet, this is the star, the orange stuff is disk. You see that the planet is slowly moving closer to the star, And the reason why its orbit is decaying and going closer to the star is because as it is moving in the gas, it is creating a wake. And this wake is interacting with the planet in a way that it moves towards the star. Okay. There is a lot more details. Type 1 can be very uncertain, but as we said at the beginning, we are not going into the details. We will stick to the storyline. Okay. Now, what happens if the planet grows big enough such that the heliosphere is bigger than the disk scale height? When that happens, it creates a gap in the gas disk. Of course, if it is in a gap, then it cannot create these wakes because it's not in the gas anymore. But it still keeps decreasing its same major axis because the whole gas disk is slowly falling onto the star because of viscosity. Okay, so imagine that in type 1 migration, the planet is creating perturbations in the disk, and as a result, is falling towards the star. When it grows massive enough to create a gap, then it stays trapped in the gap, and the whole disk with the planet goes to the star and tries to fall in it. Okay, just remember this. Another thing to remember is both type 1 migration and type 2 migration are smooth decay of orbit, smooth change. Okay, so this is a very, very slow and smooth process compared to something that I'm going to show you next. When the gas disk goes away, then you have formed fully planets in a system with multiple planets. Then over time, the planets can gravitationally perturb the orbits of the other planets. And if you wait long enough, they can become unstable. They can have this kind of orbit crossing, and there can be ejections and collisions. Okay, so of course, these changes in the orbit are very dramatic and drastic, and it is not smooth at all. It happens at a very fast time scale. The reason why it's very interesting to understand how the evolution happens after you form the planets is because the planetary systems that we see today had billions of years of this evolution process that happened after the planets formed. So one of the surprising things when we first started finding planets is that how many eccentric planets there are. Okay, so in the solar system, the eccentricities are very low. The planetary orbits are fairly circular. But if you look at the exoplanets, the eccentricities can grow all the way almost to 1. And this was a big surprise. And then it turned out that if you have multiple planets, 3 or more, or sometimes even 2 is sufficient, then the planetary orbits can become unstable, and the movie I showed you, something like that can happen. And the stability timescale. So if you ask the question, how long do I have to wait before something crazy happens in the planetary system? That depends on the so-called hill separation. Okay, you take 2 planets, you find out what is the hill, roughly the hill radius is for the 2 planets. And then you find the orbital separation, the distances between the 2 planets, and find out what is that distance in units of that hill radius. Okay. So as you increase hill separation, so this K quantity, the time scale for instability grows exponentially. And so this is time in year till instability. This is K. And you can see that even sometimes after a giga-year, planets can become unstable. And this is true for 3 planet systems. This is I'm showing you example of a simulation for 3 giant planets in one system. And of course, if you look at how, as a function of time, the semi-major axis of the planets and the eccentricity of the planet evolves, you will see that these are really crazy, and these are extremely chaotic evolution. So in this case, the green planet and the black planet collided with each other and ejected the red planet. In this case, the black planet is ejected, and then the red planet and the green planet just happily stays together. In all these different cases, the initial conditions were basically the same. So they had very low eccentricity orbits close to each other, and then they collide or eject each other, okay? And another thing you notice is, in the end, the stable planetary architecture can have higher eccentricity and almost always fewer planets, okay? So remember this. Now, what is the effect of this kind of dynamical encounters? So if you start from very low eccentricity orbits, it can significantly grow in eccentricities. Okay, so these are cumulative histograms of eccentricity. So this is the initial, this is the final. And back in 2008, for giant planets, we showed that without any fine-tuning, you can very easily explain the eccentricity distribution of the observed systems using these simulations. Okay, so this is now quite well established that the eccentric Jupiters probably are coming from dynamical encounters between planets. Let me just skip this part. And go to this. So I talked about what happens when giant planets interact, okay? But from yesterday's talk, Manoj Purvankara's talk, you probably remember that he said that the number of giant planets relative to the smaller sub-Neptune type planets is much smaller, okay? Much fewer giant planets observed. So does it mean that this kind of dynamical encounters may not be as ubiquitous in most of the planetary system? I would argue that is not correct. And this is something that we're working on now. So what I'm showing you here is the distribution of this mutual Hill separation for sub-Neptune planets we know today, okay? And so this is just a probability density function. You can see that in the large K range, the distribution decreases almost like a power law. But then something changes roughly around here, and it's sharply that the number of systems with lower K values sharply decrease. So the question is it possible that even for these smaller planets that we see more often in the exoplanetary system, even in these systems, the orbital architecture, the spacings, are determined by dynamical processes, okay? So we start with a bunch of planets with properties, orbital properties similar to observed, and we allow them to interact with each other. So this is an example of 7 planet systems that are just interacting with each other. And from previous discussions, you know that eccentricities can grow, planets can collide, some of the planets may be ejected to very large semi-major axis. In the end, you have fewer planets, and you end up having a more stable system with larger K, okay? So the question is, if we simulate hundreds and thousands of these kinds of systems, do we get orbital properties of planets similar to what is observed? So here I'm showing you, so the black is the observed K distribution. The red is the blue dot is the initial K distribution. So we create a power law type distribution for initial K. And then this solid line is the detected final planet K distribution. So you can see that if I start from something that looks very, very different from what is observed, because of dynamical processes, it can go and explain the distribution of hill spacing that we observe today. Not only that, when it matches the hill spacing, it also roughly predicts the period distribution of the observed planets, the period ratio distribution of the observed planets, as well as the radius distribution of the observed planets. Okay, so that's really fantastic. So we think that planet-planet dynamical interactions may be responsible to determine the orbital properties even for the low mass planetary systems in multi-planet systems. How long do I have now? Okay, no one is answering. Let me take a couple of more minutes. So there is another thing that I want to talk about. So this is really, really curious. Okay, so if you look at the current period ratios of adjacent planet pairs, you will see something really weird. So I'm showing you the period ratio near the ratio period near the mean motion resonance of 3:2 and 2:1. You see that there is a deficit of systems just below 1.5 and an excess of systems just above 1.5. Okay. Similarly, deficit of systems below 2.0 and the excess of systems above 2.0 is not that significant. Okay. So it really feels like, okay, so this is a little, you need to pause to understand this trend. Okay. So it is totally fine to have no feature near the mean motion resonance. It basically says that the smooth migration was not smooth enough to trap them in mean motion resonance. It is also totally fine to have excesses at the mean motion resonance. It basically says the smooth migration was efficient enough to trap them. What is really weird is that we see the excess, but not at the resonance. It's wide of the resonance. And we see a deficit that is narrow of the resonance. Okay, so it's almost as if you were taking systems that were initially narrow of the resonance and dumping them wide of the resonance. And we believe that this can be done if you have planets that are interacting with the failed planets or planetesimals in a system. So here I'm showing you two planets interacting with planetesimals, and this is how the same-major axis is changing. You can see that the same-major axes are not changing significantly. So these lines are the locations of the planets. But if you look at the period ratio, it goes from narrow of 1.5, slowly comes close enough to 1.5, then jumps across 1.5 and then keeps increasing away from 1.5. Okay. So if I play, so as a result, what you can, these planetesimal interactions can easily take systems that are narrow of the mean motion resonance and dump them wide of the mean motion resonance. And that probably is exactly what we are seeing. So we did a large number of these planetesimal interaction simulations. And here I'm showing you the end result. So the blue is what we find in our models. The black histogram is what is observed. The error bars of the two histograms, first of all, look very similar to each other, and they are consistent with each other within 1 sigma of the error bars. Okay, so all the error bars are 1 sigma, and that is true for both 3:2 and 2:1. And we find, interestingly, that for 3:2, we need roughly 25% of initially resonant system, and in 2:1, we need less than 1% initially resonant system. And this kind of constraints obviously has implications on what kind of formation process that had gone into forming these planetary systems. Okay, so that's all I wanted to talk about. So just to remind you, we talked about planet formation, different stages, really broad brush without getting into much details. We went from dust to planets. We talked about planetary evolution, and there were 2 different types, smooth migration in presence of gases. Then I talked about what happens when gas is gone and planets can scatter other planets. And then we can also have planetesimal scattering. And I believe that we are seeing signatures of all of these processes in the orbital architectures of exoplanets we see today. And I told you 3 specific stories. One was exactly how you form the compact multi-transiting systems through at the dead zone inner boundary that keeps receding over time, the inside-out planet formation. I told you how you may be forming hot Jupiters through planet-planet scattering, and maybe the separations and other properties of the Kepler multis can also be explained through planet-planet scattering. And I said how the curious distribution of period ratios near mean motion resonances in the multis may be a result of planetesimal scattering. Okay. All right. Sorry for going over time, and thank you for listening.
Thank you, Dr. Sourav. Should we take questions from the participant?
Sure, absolutely.
Okay.
So
can we allow students to unmute and ask question directly?
Absolutely. But
Okay.
do you think I should look at the skipped questions during the talk and
Sure.
First? Okay.
Yeah.
Which are the tens of potentially habitable planets characters names? There are too many, man. So this is a question from Davhade Raka. There are too many. If you go to, let me just do this, NASA Exoplanet Archive. Just Google it, and there you will see all the planets with their names and their properties, and you can find the habitable planets. Okay, sir. So this is a question from Megha. Sir, what point in the evolution of the planet do they start developing their unique properties like their atmosphere, etc.? So this is it's really hard to clearly answer this question, Megha. It's very uncertain. So atmosphere can have two separate sources. So you can have atmosphere that came from the initial atmosphere capture while the planet was growing, or you may have completely lost that initial atmosphere, and then through volcanism and outgassing and like basically in the planetary core's internal mechanism can create volatiles that can populate the atmosphere. So exactly which atmosphere exists today will determine exactly when the atmosphere was captured. Now, if you think about the atmosphere that we can observe and do, for example, transmission spectroscopy, so these are typically the hot Jupiter planets where the atmosphere are easily observable. These definitely acquired their atmosphere from the protoplanetary disk itself. Okay, so the total amount of gas on them is much higher compared to, say, the Earth's atmosphere. Let's see what. Megha has another question. Does the planet property depend on the distance from the star? Yes, indeed. Depending on the distance from the star, what kinds of materials remain solid changes, and also the protoplanetary disk properties change. So as a result, what kind of planets will form and with what material, that is dependent on the distance from the star. So was there any particular reason why a particular initial hill spacing was chosen? No particular reason. Power law distribution is as good as any. We basically don't know what the initial separations were. The point is, independent of what the initial separation was, it comes and converges with the hill separation distribution we see today. Different mechanisms of planet formation between low mass stars and high mass stars. We do not know yet, because the planet host stars, the range in masses of planet host stars as of today is rather small. So when you say high mass stars, if you are thinking of 10 solar mass stars, we do not know planets around 10 solar mass stars. So we can imagine that if you go to very high mass stars, then because these stars are much bigger, hotter, their radiation field will be much different. So the protoplanetary disk properties will be somewhat different. So it's going to be a very interesting question, but we do not know enough about it yet. We have some clues on what may happen. So for example, we know planets that formed around pulsars. So pulsars are massive stars that became neutron stars, which is now spinning and sending radio signal towards us, okay? So definitely these planets formed around those massive stars. Now, whether it formed through the mechanism that I talked about today is unclear, because there are other ways you can form planets at a much later stage as well. So the bottom line is it's very uncertain, and maybe that itself can be the purpose of a different talk. Okay, so I think I have finished all the typed questions. If there are more questions from the audience, I'll be happy to take them.
So we request participants to raise their hands, like if you want to ask questions, so we can take it one by one.
Prachi, you decide who is asking? Can you decide who is asking, or should I?
No, they will raise a hand, Sourav. Like they can ask. I mean, we have changed the settings so that they can raise the hand and they can ask question directly.
Okay.
We are waiting participant to raise their hand.
Actually, there is already another question from Bruno. So one more. So he asks, do planets affect host star evolution as well? This is a fantastic question, and the answer is it depends, and in some cases probably. So just imagine a scenario where you have created these compact multi-planet systems like we observe today, right? And the host star has now become a giant, gas giant, not gas giant, but a red giant. Okay, so too many different types of giants in this talk. So red giants are stars that leave their main sequence and rapidly grow their size. So in the red giant phase, the sun will probably grow roughly 200 times in its size. Okay, so that's just ballpark numbers. So clearly, when the host star leaves its main sequence and expands, it'll engulf all the compact multis, okay? Now, what will happen when all of these solids are dumped onto the star? That is going to be a very interesting question, and people have looked at it. It depends on on detailed calculations, exactly how big the convective envelope is, how much the mixing is, where do these solids end up. So there is a lot of details that you need to take care of. In fact, there are some interesting recent observations. I do not remember the names of the authors, but you can easily find out. These are white dwarf pollutions. Okay, so from white dwarf, the people were observing the white dwarf spectra, and they were finding that there seems to be a lot of dust and pollution on the white dwarf surface. And the question was, where is this dust coming from? And is it from a debris disk around the white dwarf? Is it fallen planets and so on? So there is definitely a lot goes on in a planetary system around a star than what I presented today. And that's why it's so interesting.
Yeah, thank you, Sourav, for the answer. Participant, we again request you, if you have a question, please type it in the chat box, or you can unmute yourself and ask a question directly to Dr. Sourav. Dr. Ravi, do you have any comment? Like,
I was just waiting for people to finish their questions, so I'm just being quiet. I see there is something else.
there's one question. Yeah. So should I go ahead, or Dr. Sourav, you want to read and?
I can read.
Okay.
Thanks. Remember, I kept saying that details matters, and I am not going to talk at all about details. Indeed, what the core mass can be, like how big the solids can become, that depends a lot on the local conditions and exactly how you're assembling the solids and what is the supply side of the solids. Okay, it is not surprising to find 40 Earth mass rocky systems. In fact, we don't even know what is the rocky or the core mass of our own planet Jupiter or Saturn. So we roughly say that it may be of order 10 Earth mass of solid core inside the Jupiter and Saturn, but it's of order 10. And since in this talk we are talking of order, so 40 Earth mass solid TOI 849b is also of order 10. So factor of 4, we do not worry. But this, in terms of the details, this it's thanks Ravi. What? Well, so okay, I am biased, but if you think that inside-out planet formation may be a mechanism, then once you form the ring and you have collected all the solids in the ring to create a planet, how much the planet will grow and accreting what, that depends on the details of the supply. It can accrete the atmosphere, or it can keep on accreting more solids if the solids keep coming to the same dead zone inner boundary. Okay. In principle, you can see, so this this dashed black line, that is if you go on having a solid dominated accretion. Okay, so I did not explain all the different lines because I did not, for this talk, I was not interested in the details. But you can see that depending on where you form and depending on exactly what accretion rate or what property of the protoplanetary disk you assume, you can have wide range in solid masses. So this blue dashed line will be also solid dominated accretion. So all the dashed lines are solid dominated accretion with different accretion rate. And since it's a G star, if it's very metal rich, if it's a metal rich G star, I can imagine that you can maybe form something like this through inside out. So this is going into the details because Ravi asked the question. Ravi, is that satisfactory?
Yeah. So I was trying to find the age of the system for this TOI 849 to see if atmospheric erosion could have happened on this closed-in planet, just to make sure that it was indeed that could have played some process there. But what you said is really good.
Yeah, this is a cool system, man. I didn't think about it before.
That's right.
Thanks.
There's another question.
Yeah. So planet is part of a binary star system. Does one star impact the planet's evolution more than the other? And why is it so?
Maybe we could ask Megha to clarify the question. When you say the planet is around the binary star system, are you asking if the planet is around both the stars, or are you asking if the planet is around one of the stars? You can unmute and speak up. Megha, you can unmute and clarify the question if you want. Or maybe Sourav, you can just address both of them.
Okay. Yeah. Okay, so there are two things that I don't quite get. So one is, as Ravi was pointed out, planets can be a circumbinary planet, like the two stars, and then the planet is going around both the stars, or the planet can go around one of the stars, and the other star may be outside and going around the star planet system. Okay. So the other thing that I do not understand is what you mean by does one star impact the planet's evolution more than the other, and why is it so? So depending on the architecture, the protoplanetary disk may have belonged to both stars or a single star. If it is around a single star, then of course I would think that the disk that the planet was formed in, that star will have a higher effect in terms of what went into the planet. But if it is a common disk around the binary, then I would think that the material that goes into the planet will be common to both the stars in the binary. But it can have many variations depending on the details of the architecture. For example, if the companion stars in the binary have very different masses, then the stars in the binary will have very different properties. And as a result, the disk itself will be a combination of the different stars. The material from the different stars. And so, for example, a high mass star will have higher ionization capacity, hotter temperatures, and it might control the disk properties more than a lower mass star. So that is if the companion stars in the binary have different properties. Does it kind of answer your question?
Yes, sir. Yes, sir.
Okay.
Thank you.
Any other question, participants? So we have changed the setting. If you want to ask question, you can unmute directly and ask questions. Yeah, I think we don't have any questions. Dr. Ravi, do you want to make any comments before closing?
I think we are good now. And if you see no other questions, then I think we can end the session.
Sure, sure.
Yeah.
Only just to remind participant that the next session will be on Wednesday. That is on 15th of February by Dr. Sujan Sengupta. So the time will remain same. So we can start the session around 4:30. So all the participants can join around 4:25. So thank you again for joining this session. Thank you, Dr. Sourav, for this wonderful talk and, answering all the questions. And thanks, Dr. Ravi, for, having, attending all the sessions with us. Thank you once again. Thanks.
Thank you. Thank you
Yeah.
for having me here. It was a lot of fun.
Thank you, sir. Hope to see you soon in the next meeting or so.
Yeah.
Yeah. Thank you. Thank you.
Bye.
Yeah,
Bye.
I'm signing off. Yeah, thanks.
Bye. Thanks.